Hi, everybody. This is Nalini Elkins with Industry Network Technology Council. I hope you can all hear me okay. Once you go ahead and send me a message if there's any problems, and we'll go ahead and get started. We're happy to about a webinar we're doing today, Quantum 101 by Dr. Bruno Avertzer. I'm looking very forward to this. If you have questions or anything, please feel free to put them into the chat window. I'll be monitoring that. And just so everybody knows, we are being recorded. Okay. So let me tell you a bit about the organization. We are a nonprofit. We bring together large end user organizations as well as academia and government to understand standards, because internet standards impact everyone. They impact not just the internet, but the large corporate networks that many people run. We collaborate deeply with the India Internet Engineering Society, which tries to bridge the gap in India, uh, doing the same things, but more from a developer point of view. The idea is to bring more and more people from India into developing internet standards. Yes. We've received a bunch of grants, both from Aaron and APNIC. Those are the internet registries, the people who give us all our internet numbers. They have been mostly on IPv6 because that is what we have been focusing on. And if anybody should feel moved to donate to us, please feel free. We are a nonprofit. So we've done a bunch of different things. We started for a number of years. We did IPv6 deployment. We've done a deep dive into cybersecurity, cryptography, and so forth. Our latest series was new work at the IETF, including space protocols, which everyone seems to be talking about today. And this series is on quantum technologies. Our whole series is as follows. We have quite a few things going on, as you can see. We're very happy to have people such as NIST speaking with us, and a special talk by Vadim Lubashevsky of IBM Research. He did some of the core algorithms in post-quantum cryptography. So just a few words about me. We'll just skip past that very quickly. I've been involved in this whole world for quite a bit of time. But let's talk about Bruno. Bruno is the quantum theory lead at Leidos, and he also is vice chair of the QEDC. The QEDC is a forum for bringing together many folks who are working in the quantum industry. I believe it's a U.S. Department of Commerce who is heading that up. It's their quantum initiative. Actually, that's where I met Bruno. And today he's going to be talking to us about getting started in this whole world of quantum, what it is, and where we are. So, with that, I'm going to turn it over to Bruno. Thank you so much.
Thank you, Nalini, for that introduction. I'm going to start sharing some slides. So can everybody see what I'm sharing?
Yep.
Okay, great. I have a little laser pointer too. All right, so my name is Bruno. I'll be talking to you today about Quantum 101. So intro and a little bit of a deep dive into the various areas in which we expect quantum technologies to change how we view the internet and maybe even broader things than that. So I am the vice chair, as Nalini said, of the QDC Standards and Performance Benchmarks TAC, and I'll be presenting in that capacity. You can find my contact on that website if you'd like to ask me any questions afterwards. But I want to add a disclaimer that any opinions I express here are my own and do not represent the positions of Leidos or the QEDC necessarily. All right. So first, I want to talk about the history of quantum computing. When I think about the history of quantum computing, I break it down into these three eras, which are basically characterized by experimental progress of the platforms. The first one is this area of quantum computing theory. which is where there are no real experiments showing the quantum computing milestones, but there's a lot of theory being developed on how that might happen. It starts all the way in 1900 when Planck posited that light was quantized, that its energy spectrum was discrete and not continuous. There are only certain values of energy that light could have. This was the first kind of quantum thing that had even been talked about, and this is what kicked off the quantum revolution. It got really intense with this idea of EPR, Einstein, Podolsky, and Rosen's, sorry, um, which examined the idea of quantum entanglement. Now, Einstein thought that quantum entanglement was a knock against the quantum theory. He thought that it was not a very good idea, and he thought this disproves the quantum theory. But it turned out that some years later, a guy came along called Bell, and he said, actually, what Einstein pointed out about entanglement is true. This idea that particles over a long distance can be fundamentally correlated, even at faster than light apparently speeds, is not incorrect, and it's a fundamental feature of quantum theory. And this is what created the basis for all the developments that followed. Clauser first showed this actual property taking place a few years later, and quantum computing built off this idea with some theoretical developments in the 70s, but really popularized by Feynman in the 80s. So this happened, and in 1984, there was some very impressive work on superconducting circuits, which nowadays realize quantum computers, for which Martinez and Shokov won the Nobel Prize quite recently. So this is the era of people thinking about quantum computing, but later on, there started to be early experiments of actually demonstrating quantum computing. And this was kicked off by Shor's invention of two things in 1994 to 95, Shor's algorithm and quantum error correction. So before this time, quantum computers were kind of a curiosity. People had shown that they could do interesting things, solve interesting computational problems, but not that they were useful. Now, Shor changed that because he showed that quantum computers create a vulnerability in RSA, that they can solve the discrete log problem, and that therefore they can basically recreate someone's private key from a public key if it's encrypted using RSA. And that made people pay a lot of attention to quantum computing. Now, even after this, no one had any idea how you scale a quantum computer because qubits are very noisy until Shor solved that problem 1 year later with the idea of quantum error correction. So this is what kicked off a series of early experiments, such as IBM's demonstration of factoring in 2001, led to the creation of early companies like D-Wave around this idea of quantum computing. There are a couple of other early experiments and theory breakthroughs in the 2000s, but quantum computing as a field got a lot of investment in the 2010s, starting with Google's investment in the Martinez Group, which later won the Nobel Prize, in superconducting quantum computing. And then a lot of experimental milestones started to be demonstrated in this NISQ era, right? This early experiments era, you have maybe factoring 15, which is not super useful. But here in 2019, in the noisy intermediate scale quantum or NISQ era, right at the midpoint, I would say, Google demonstrated something called quantum supremacy. They claimed that they solved the problem faster than any classical computer could ever hope to, by orders and orders of magnitude. Now, this claim was later refuted by IBM, but it really showed that quantum computing had legs as a technology. So there were a lot of other milestones here in this noisy intermediate scale era till we got to the early fault tolerant era very recently, in my view, with Google demonstrating some key milestones in quantum error correction and a couple of other demonstrations that have come. So this whole timeline spans a period of over 100 years. And in the meantime, the information age is progressing with developments like the transistor and information theory. You think about it, it's actually not the first thing on this timeline because quantum physics is so old. But also things like error correction, basic computing milestones like the UNIVAC, development of the MOSFETs, machine learning with the perceptrons, all the way to the commercialization of the internet, creation of edge devices like the iPhone, and booms in machine learning and AI. So all of this has happened while quantum computing was still finding its legs as a technology. Okay, I need to switch to the mouse, I guess. Okay, here we go. So all of these quantum concepts that we've talked about have classical analogs that come from the developments of the information age. Just as there are classical bits, zeros and ones, there are quantum bits or qubits. The key difference between these things is that bits are integers and qubits are vectors. I'm not going to go through this whole table, but the gist of it is that every milestone, or many of the milestones that have been significant to the information age, have been reconceptualized for quantum information devices that are based on entanglement. And these all have key differences. Like in error correction, you compute on encoded information without decoding, which is different than how you do forward error correction usually. Different limits of quantum repeaters compared to classical repeaters, and so on and so forth. But to really understand all these technologies, we have to dive a little bit into quantum information theory, which I'll try to explain at a pretty high level. So the quantum information revolution is based on this concept of entanglement. Now, entanglement is just a statement about information. Information means bits. So you can imagine anything that can be a bit. It can be a transistor. It can be a quarter. It can be anything that has two states, right? And if it's a quarter, we can label one of those states as 0. That could be heads. And the other one would be 1. That can be tails, right? So a quarter has two states if you want to use it as a bit for computing, 0 and 1, heads and tails. Now, if you want to use it for quantum computing, you have to start thinking about states that are in between 0 and 1, which you represent with this plus. So you can imagine that instead of being 0 or 1, a quarter is something in the middle. It's like on its side. And we haven't figured out what side it's going to land on yet because it's still standing in the middle. You call that a 0 plus 1. This is a superposition state. The other thing is if you have two quarters. Normally, you would flip these quarters independently and they would land in some assortment of heads and tails for possibilities, right? But if your quarter represents an entangled particle, then you have two quarters which are correlated in this way. They can only land together. They can either both be heads or they can both be tails. So we talk about this as a 0, 0 plus 1, 1 state, as compared to the 0, 1, and 0 plus 1. And that's because the two outcomes that you see here are both heads or both tails, like they're glued together by popsicle sticks, right? So the key point here is that information is information. If you flip a coin, at the end of the day, it's going to land on heads or tails. And the same thing is true of a qubit. When you measure 2 qubits, there are only certain states that it can end up in, the 0, 0 or the 1, 1, the 0 or the 1, depending on how you arrange them at first physically, right? But that is what's going on. Now, these ideas lead to the ideas of quantum logic. So you have classical logic gates such as the NOT gate, which takes 0 into a 1, right? Represented by this inverter. You can find the truth table here. Now, there's also a quantum NOT gate, which is this Pauli X operator. So this blue thing that I've highlighted here tells you how a quantum state is transformed by this operation. And you can see that it's exactly just this truth table, right? 0, 1, 1, 0, 0, 1, 1, 0. You also have a quantum analog, sorry, of the classical XOR gate. So quantum operations have to preserve quantum information. They have to be so-called represented by unitary matrices, which means that they can't have two inputs and one output like this. They have to have two inputs, which are these two wires, and two outputs, which are these two wires. So the matrix looks a bit different, but it's essentially the same operation. Now, there's something unique about quantum information, though, which is this phase matrix, this red one here. So this idea of phase speaks to a degree of freedom that isn't possible to represent classically with just one classical bit. If we think about the different positions of states on a coordinate axis, you could say, this is the 0 state, this is the 1 state, this is heads, this is tails. You have something in between heads and tails like this, 0 plus 1, and then you have something on the other side. What if the coin was rotated, right? This could be 0 minus 1. And that's just subtracting these vectors, right? This is just a 0 vector minus the 1 vector. This is just a 0 vector plus the 1 vector and then normalized to be a unit vector. So you can think about these as two different rotations of the coin that's on its side and hasn't collapsed yet. And those two different rotations are represented by this different sign. You can rotate it even more finely, and then you'd have a complex phase instead of just plus or minus 1. But these are the fundamental building blocks of quantum logic. Now, these quantum logic units are represented when we do computing by quantum processors, of which there are many different types. The four that I think are most prominent today are photonic, superconducting, trapped ion, and neutral atoms, represented by a variety of companies and with various trade-offs in terms of the efficiency of the technology. So each one of these has their pros and cons, and we'll talk about that a little bit later, but these are maybe the four main types of quantum processors that we have today. Now, today, I would say that we are at the tail end of the NISQ era or in the early fault-tolerant era, and each of these processor types was represented well in that era. So the NISQ era is characterized by noisy intermediate-scale quantum devices, generally considered to have fewer than 200 of these qubits represented by atoms or photons or ions or superconducting circuits that you do computation on. So less than 200 of those physical things, and a gate error rate, meaning a logical gate, like we talked about before, between 0.1 and 1%. Compare this to a transistor, which for a logical operation has an error rate of 10 to the minus 15th or something like that. So the takeaway from that should be that these are noisy machines. You can sample from them. You can see this connectivity graph that tells you the different noise rates. You can do measurements. You can do some basic things. This is like an IBM connectivity graph. You can sample from the states of this machine, and it's a pretty decently sized machine. It has a couple of these qubits. But if you want to control it well, as well as we control classical devices like transistors, you are not going to have a good time. So that's the NISQ era. And then there's this quantum supremacy milestone that we briefly talked about. This was demonstrated with a 53 qubit device with 1% gate error. So definitely a noisy device, right? The idea was that you run this random circuit sampling task. You take this very long quantum circuit that's designed to be very hard for a classical device to simulate. And then you say, okay, well, no classical device can simulate this thing. It would take the world's best supercomputer 10,000 years to run this algorithm. And this is, by the way, like at the time, considered a useless algorithm, right? And even that claim of difficulty was later debunked. So I'm trying to make the point here that we are not in the point of having super useful quantum devices. Now, if we did, we could think about these quantum algorithms. We have Shor's algorithm, which leads to this concept of QKD. We have quantum simulations of materials that will help us to design more resilient materials, for example, to drug discovery. And then we have things like quantum machine learning. Now, quantum machine learning was basically killed off. It was very popular in the 2010s because of the machine learning boom, but there were some results that made it very difficult to imagine that we would have a real advantage there in terms of speed, like what IBM and Google have talked about. But there have been some recent advancements that throw this into question. So excited about any developments in QML, take it with a grain of salt. You need error rates of 10 to the minus 10, and we are not nearly there for any of these algorithms. So how do we get there? The idea is to use these things called logical qubits, which are error-corrected qubits. Take a transistor, it has an error rate of something like 10 to the minus 15. If you look at the best quantum devices today, they have error rates consistently through the device of something like 10 to the minus 3, maybe 10 to the minus 4. Okay. So these are usually trapped ion devices. Now you can improve these error rates by using what's so-called error correction. These triangles represent different arrangements of ions, for example, in not physically, but in terms of the gate operations you apply to them. So if I count them up in this picture, each of these white dots is an ion, right? So you have 1, 2, 3, 4, 5, 6, 7 of these ions in this D equals 3 code. D equals 3 has 7 ions arranged in some way with logical instructions that can take your error rate down a lot. So if you have a physical error rate, which is P error, and then you have a threshold, which for this kind of error correcting code is something like 10 to the minus 2, then your actual logical error rate is given by this expression here. So if your physical error rate is 10 to the minus 3 and your threshold is 10 to the minus 2, that gives you 10 to the minus 1 here. Distance is 3, so you have 2. So your logical error rate is not great, right? But as this goes up, as you have bigger and bigger arrangements of qubits, physical qubits, then you get better and better performance because your D values keep going up, right? So the number of qubits you need for this code for a given D value is something like D squared. That's just the arrangement length times height that you need to make these bigger and bigger triangles. And this is what leads to something called the threshold theorem, which says that if you are under this threshold error rate, then error correction improves your performance with the distance, and you can eventually make really, really efficient devices. This is what people are trying to demonstrate today. So you have a bunch of companies making hardware and a bunch of companies making algorithms and software to run on those devices and make them run better using, for example, quantum error correction. So state of the art today is something like 300 physical qubits with a 10 to the minus 3 error rate and with efficient magic state distillation, which is something we haven't talked about, but it's a fundamental primitive you need to do useful quantum computations. The problem is that they're not on the same platform. One of these guys is 300 physical qubits, one of them has 1 e minus 3 error rate, and one of them can do magic state distillation. So if the same platform could do all three, then maybe we could perform a 1-qubit quantum algorithm using error correction, which would be really cool. But a useful quantum algorithm requires something like 80 qubits, right, at the bare minimum. They can be noisy, but if you want to do a logical quantum algorithm, it's not close to that point yet. So something people use to say maybe we can get around this is this idea of distributed quantum computing. So quantum computers today maybe are not large enough to run these full optimized error-corrected quantum algorithms. But if you actually network them together, like we network distributed classical computers for, distributed workloads in data centers, then you might have enough qubits in your system to do something useful. This is something that hasn't been demonstrated at scale, but it's a key part of how many companies are trying to get to quantum advantage. So what is quantum advantage? It's demonstration of useful quantum algorithms is the subject we're talking about. Um, Kind of like what the Google claim was before, although that one was called quantum supremacy. These terms change a bit, but we've had a lot of presentations in the QEDC about what quantum advantage is and what each company thinks it should look like, right? So we've had some companies that talk about supremacy, advantage, and utility alongside each other. Some that talk about the quantum advantage era and how many quaps, as an analogy to flops, we have here, and different kinds of quantum advantages that you can have. So this has been really great. If you want to see the current status, I urge you to check out IBM's Quantum Advantage Tracker, which keeps very good track of all these things. But the takeaway from this set of webinars that we held in the QEDC is that there is really no consensus on quantum advantage, on what quantum advantage is. And so the associated question is, how will we know when we have hit quantum advantage if there's no consensus? And so you hear perspectives like when we can prove it mathematically, right? You can say when we can sell commercial quantum computing services, is quantum advantage a mathematical thing or is it a metric for cost, right? Some people say when we have a useful application where we beat the current best known classical algorithms, right? I think this is a popular position today. But there's an option D, which is when it actually has impact, like when someone forges all of our private keys and causes Q-Day. So let's talk about that a little bit more. Q-Day is the day when quantum computers can break a big enough cryptographic primitive, like RSA 2048, to cause cybersecurity impact. Now, NIST has a bunch of PQC algorithms it developed, which, unlike RSA, are assumed to be safe against quantum computer attacks. But there's no proof of security, right? It's quantum computers, or even classical computers. And when
Andre, we have lost Bruno. Just give us a minute. He's reconnecting.
All right, so what is Q-Day? Q-Day is the day when quantum computers are big enough to cause cybersecurity impact. They can break a large cryptographic primitive like RSA 2048. Some people might say ECC instead, right? So the NIST has a lot of standards around PQC algorithms, which, unlike RSA, are supposed to be safe against these attacks. But there's no proof of security for these algorithms. It's in theory possible that some or all of them will be broken by quantum computers. And if that happens, then we won't have any algorithmic-based security to rely on. And there will be no quibbling over definitions of quantum advantage because everyone will know that things have changed, right? So that's a very scary thought. And people have been thinking about what mitigations we might have. So all these vulnerabilities are based on the assumption that we're using algorithmic encryption. So that's stuff like RSA, which is based on the difficulty, the complexity theoretic difficulty of some computational problem, like factoring a product of primes, right? So people use this because it has strong security properties, and the overhead is entirely computational, but very simple to implement. So a very large majority of use cases in the world use algorithmic-based cryptography. So the other things you can do are things like physical layering cryptography. So something like spread spectrum communications, where you spread your signals over a wide frequency band, right? And so this has a little bit less security. The idea is that an eavesdropper has to guess the right frequencies, but in theory, they can do that, right? It's not some NP hard problem. And it has a high overhead. It's bespoke hardware required, and it's complex to implement. So some people still use this, like military tactical networks, RF comms, but it isn't widespread in use at this point. And there are still attacks against it, like just intercepting the signal. It's difficult, but possible, right? Now, you can add quantum on top of this. So it's a quantum physical layer security, like quantum key distribution, or there's some other methods. So it's a physical encoding that is guaranteed by quantum security properties, this idea of entanglement, right? So if you have a 0, 0 plus 1, 1 state, like what we talked about before, with only two outcomes, you can use that to direct that physical property to derive unconditional security guarantees, which if you do entanglement based or device independent is sometimes called QKD. It is a really an unconditionally secure thing if you implement it correctly, right? But the overhead here is very hard because not only do you need bespoke hardware, you also need to implement this non-standardized algorithm. You need to like rethink your KMS. You have to do a lot of things, right? So it's very complex and mostly only used by banks or ultra secure networks. And even then, for the non-device independent versions, there are attacks that you have to worry about, like physical layer eavesdropping, photon number splitting if you have a multi-photon quantum state, detector blinding that creates a vulnerability. It's not that this is some kind of magic, right? But this is what quantum physical layer encryption is. So quantum networking advantage is something that provides a key advantage, no pun intended, for securing cryptographic systems via things like QKD, right? Some people will say these keys are unconditionally secured by no cloning theorem, no matter how you do QKD. Don't believe this. There are lots of side channel attacks that you can make against lots of different types of QKD systems. Now, with great difficulty, you can write a security proof for a specific implementation of a QKD system. But these keys generated by entanglement or device-independent QKD systems are a lot easier to prove that are secure. It's a much simpler process. The thing is, we don't have very good DI-QKD systems anywhere, so provably secure quantum cryptography is really difficult in practice. Technology isn't there. It's mostly due to loss in fiber optic channels, which severely limits the range over which you can do this kind of thing. Now, there are other methods as well. QKD is not the only method of secure quantum comms. So there's quantum secure direct communication, which is something that I really like. The idea is instead of generating keying material to replace your algorithmic security, your algorithmically derived keys, you can transmit data bits directly in the physical layer with the same security guarantees that you get from entanglement if you do it properly, right? So this is something that is nice because you don't have to rethink your whole KMS system. You just have to rethink the physical layer implementation of how you do comms, basically like re-architect your ONTs, right? There's quantum computational key generation, where you actually use timing constraints and the computing speedup that quantum computing gives you to generate keys and security. So this is a really exciting recent idea that I encourage you to check out. The takeaway here is that there are a lot of different approaches with trade-offs, and organizations are finding that crypto agility is becoming very important. So issues with quantum secure comms, there's this very famous NSA memo highlighting all the issues with QKD. Some of them have been resolved, at least partially, since this memo has been put out like 5 or 6 years ago, but some of them are still real issues today, like increasing the risk of denial of service. I mean, there's no doubt that that's the case, right? You have a much lower generation rate with these systems. It requires special purpose equipment. That's certainly always going to be true, right? And the distance one is the one that's been overcome the most, which is by progress in quantum repeaters. So these are devices that, just like classical repeaters based on EDFAs, increase the fieldable distance of communication solutions, just quantum communication solutions. Now, there's a fundamental loss limit that these things have to be placed every 15 kilometers because they can't overcome loss above 3 dBs, which happens at 15 kilometers. That's not for every single application of quantum networks, but if you want entanglement to survive perfectly past this stage, kind of like what happens essentially in classical networks, that is how often you need to place repeaters. So there are usually two kinds of repeaters that are talked about. There are two-way repeaters and one-way repeaters. So this Gen 1 two-way repeater is based on having some midpoint between two nodes that you want to talk to, which reduces the distance by a half, right? So this is something that was demonstrated recently by Cisco and QNect in New York City, which is a very exciting experiment, right? Generation 2 repeaters use quantum error correction. They go one way. They just error correct and propagate the state along the fiber at each node, right? So it goes from 1, you correct any errors, hops to 2, correct any errors, hop on, hop on. And no one has ever done this as far as I'm aware. There are no successful demonstrations of a Gen 2 repeater to date, which is not surprising because even in much more advanced quantum computing systems, error correction was only demonstrated like 2 years ago and a very limited kind of it. So the issue with these quantum repeaters is that they still have to get around this 3 dB loss limit. Because of that, you have to place them every 15 kilometers, which is a very unappealing proposition to install this new hardware. So maybe the best way of getting around this limit is just to go to space. So you go to space, you come back, and maybe you actually don't need repeaters everywhere, right? Especially because free space optical comms are often more secure and less lossy than fiber optics. Now, it's very rate limited for the moment, but in principle, this is also a great way of generating remote entanglement via swapping in a centrally accessible location, right? What's more centrally accessible than a satellite? So these are exciting developments, but quantum networking advantage as a field is really broad. We talked about quantum networking advantage for security, and we talked about networked quantum devices a little bit. But there's also things like decision advantage in networking classical devices, things like Byzantine agreement performed with quantum states. And there's a whole list of these you can find in a protocol library online, Quantum Protocol Zoo, right? Encourage you to go through them if you're interested. But the key point is that all these advantages are not really complexity theoretic in the sense of quantum computing advantage, right? There's some complexity theoretic guarantee about how much more efficiently you can factor products of primes on a quantum computer compared to a classical computer. And that's not really what's happening here. These are fundamentally new applications that are enabled by quantum information properties, not just faster execution of the same computational tasks. So take two, what is quantum advantage? So computing, you see on the left, requires entanglement, lots of modalities, and fundamentally based on quantum computational complexity and efficiency. Networking is possible without entanglement, some variants of QKD. It's one modality, photonic, and it enables fundamentally new applications as opposed to computational complexity. But what do they have in common? Advantages are achievable before error correction milestones, but error correction is a key part of scaling these systems because error correction is really something that protects the lifetime of a quantum state. It protects the quantum information by lowering the error rates that it has to overcome. Another one is that these are mutually enabling. Just like quantum computing is its own standalone technology, it's enabled by advances in quantum networks. And the most key commonality is that they both leverage quantum information via entanglement to provide all these novel application settings. So what about quantum sensing advantage? This is something people talk about a little bit. Sensor performance today is really good. We have a lot of very good sensors, very cheap, that we use in all of our devices like smartphones, IoT, everything else. Now, it's possible that you can increase this performance using an atomic system, but is that a quantum system? I mean, that's subject to debate. If you use entanglement, you can get a really truly quantum sensing advantage. But as far as I'm aware, this hasn't been demonstrated in an operationally useful way to date. And even if you could, the biggest challenge for quantum sensors, arguably, is just competing on cost with these very good and efficient classical sensors. But there are some interesting applications. So MagNav is something that was developed in the 2000s, the idea of magnetic navigation. So usually we navigate in our cars using GPS, right? But what do you do if you are in a location that your GPS fails? Maybe you're in a bad patch of service, or maybe you're like overseas. Maybe someone is jamming your communications, right? In these environments, GPS denied environments, you can actually navigate by using the sensitivity of quantum magnetic field sensors to the Earth's magnetic field. So if you map out the Earth's magnetic field everywhere in the globe really well, then if you can really finally resolve that field, you can also know where you are, is the idea. So this was first demoed in the 2000s, and it's an application of quantum sensors that doesn't need entanglement. And I think it will be very popular in coming years, especially with, different kinds of devices that are being used in the field nowadays. Now, what about entangled sensors? So the first question you ask is, how do you entangle sensors? It's basically the same way that you entangle quantum computers to do quantum networking. It's using a quantum interconnect. So you take two atoms, you prepare them in this 0+1 state that we've talked about, right? It's what you see here in this picture on the right. Now, these atoms emit photons when they change energy. The energy of this photon is entangled with the energy of the atom. And so if you entangle these photons together, like in this bottom picture, like magic, these atoms themselves will be entangled too. So you got two atoms, they emit a photon, entangle these guys together, and now the atoms are entangled. This is called entanglement swapping, and it's the basis of a lot of interconnect concepts like what you see here in a paper from Liu et al. And then you have the question of how to use this for sensing. So if you create a Bell state of sensors, which is just the name of that 0, 0 + 1, 1 correlated state that we talked about before, if you measure these independently, it's a greater sensitivity system than taking two independent atoms and measuring them. And that increases with the number of sensors quantified by the Fisher information. The more sensors you add, the more your sensing advantage actually increases. But we're very far from demonstrating this with any non-trivial value of n. So classical sensors are winning for now just because we can put more of them together and use them, right? There's this idea of error-corrected quantum sensing, which if you use a large entangled error-corrected state, could provide potentially an SNR advantage. So the issues are that error correction is a very primitive technology, and it's a lot harder in a fielded quantum system compared to an isolated quantum computer. So there are a lot of no-go theorems on this as well, but there are a few spaces that might be interesting, like rare event sensing. If you have very, very infrequent signals and you care more about making your sensing qubits last longer in terms of coherence than having them be very sensitive, then that's something where error correction could actually be very useful. But this is a very early stage development. So we've talked a lot about various kinds of quantum technologies. I think there are still some unanswered questions from this talk. When is a quantum communications protocol secure? What is quantum advantage? And what is a logical qubit, right? What makes a sensor quantum as opposed to just being a better classical sensor? And I think that's why we need standards, metrics, and terminology surrounding these technologies. So some companies might push back on standards that affect their technologies, But the way we talk about these terms is too fraught and too disparate across different areas of the sector, in my opinion. I think we really have a need for standards. Now, standards in quantum largely don't exist. We're mostly in the definitions and talking kind of stage. So the main technology that has been standardized in like this space is PQC, which has NIST standards resulting from this long NIST competition for new algorithms. But it's not a quantum standard because this is just a classical algorithm that you implement, which is supposed to be quantum proof, right? This thing isn't using entanglement. It's just like a different classical algorithm. So I don't consider that a quantum standard, but there are several quantum standards making bodies such as NIST, IEEE, ETSI, et cetera, ISO, right? The QEDC standard stack, which I'm a part of, while active in the standards and benchmarking space, is not itself a standards making body. So within the QEDC, what we talk about are standards and definitions around emerging technologies like this, like quantum interconnects, distributed quantum computing, et cetera, et cetera. And there's a lot of interest in standards and public comms surrounding quantum error correction codes as well, which is motivated by this question of what is a logical qubit? Every company has a different claim about what a logical qubit is in their systems, right? And how do we compare these implementations to each other? So there's a question of where are these standards going? So I've been pushing this quantum advantage within the QEDC, this talk, because I think consensus on what quantum advantage is and looks like will solve a lot of these problems and open up these questions. So once someone demonstrates a fault-tolerant quantum computation with clear quantum advantage, like de facto, you have a standard baseline for what quantum advantage is and also for what logical qubits are, because that's what you use to do this computation, right? Now, when Shor's algorithm can be executed, or potentially if PQC looks more vulnerable than it does today, then quantum communication standards, I think, will naturally arise because people will be interested in how to implement these things securely, right? And I don't think we'll ever really agree on what is or isn't a quantum sensor. We'll just have sensors that are marketed as quantum or not marketed as quantum. But if entanglement enhanced sensing ever makes it to market, who knows? Maybe I'm wrong about that. So there are some questions that are also, I think, less on people's radars than the ones we talked about just now. And this is motivated by my personal opinions. I've seen that quantum follows all these classical trends. Whereas we have information theory and Shannon theory, we have a quantum information theory as well. We have bits, quantum bits, transistors, quantum transistors, computers, quantum computers, distributed networks, and distributed quantum networks. We even have machine learning and quantum machine learning. I think that this is actually really bad branding for quantum as a technology. I think quantum has to break free of this trend and come up with something that's really fundamentally different than what's possible classically. So one thing I think is quite possible is quantum human-centered interfaces, right? So up to this point, technology progress has been driven by making our lives easier, right? We have things like Uber and DoorDash and Cash App that take human functions that were previously difficult and make them easier using technology. But as AI becomes a bigger part of how we live our lives, I think we will integrate more tightly with these systems and start to reimagine our relationship with the digital world. I mean, potentially, I think we'll do a lot of tasks in the digital world in something like 50 years, and that the way we think about these tasks will be based on quantum reasoning and not classical reasoning. The starting point here is something like natively probabilistic reasoning. Instead of thinking this is an object, you could think there are two possibilities for what object could be here. Maybe it's a hand, maybe it's the window behind me, and it's something in the middle, right? And thinking about that probabilistically. And once we do that, we can move to quantum probabilistic reasoning, which is some way of thinking about what quantum information really is. So I think a lot of research needs to be done on what this looks like, but there are some early variants like quantum chess, which you can find online, which I think this will actually be a starting point for a fundamental reimagining of how we interact with digital systems. So that is my spiel. Thank you for listening, and I'm happy to take any questions if there are any.
Thank you so much, Bruno. This was absolutely amazing. So, if there's any questions that people have, please go ahead and put them into the chat window. Or if you want to talk, please raise your hand, and I think I can unmute you. But let me ask you some questions while I'm looking at the Q&A. So let me ask one. if you want to go ahead and start talking about that, and I'll get prepared with the others. So one of the folks asked, it sounds like entanglement is key to this whole business of quantum anything. So it, I I guess the question is, it's not really possible to separate that from qubits. So if you think about, I mean, you can't say entanglement is this far and quantum computing is this far, or qubits is this far. Is that kind of true?
So I think entanglement is fundamental to using quantum technologies in a way that can't be replicated classically. Now, there are some exceptions to this. There are QKD systems that can be built without entanglement, right? And so applications of these QKD networks, there are a few, but for the really interesting ones, for any kind of useful quantum computation, you actually need a lot of entanglement, right? You can think of a qubit as not necessarily entangled with other qubits, but if you want to do something useful with it, you really can. Like you really can't think about it like that, like you said, Nalini. So I agree. I think these are very interconnected concepts in the sense of the development of quantum technologies. People generally don't talk about like entanglement milestones in quantum computing because the bottlenecks there aren't really like, I guess you can think of them as being what is the biggest entangled state you can produce, which is related to how many qubits that you have. But there are other fundamental architectural bottlenecks that are difficult there. In quantum networking communications, entanglement is really the thing that people are after, and I think it really can't be thought about independently in those contexts.
Great, thanks. So here's one, and I'm going to go ahead and read this to you because it's quite long, and I think it's super interesting. So this gentleman would like to understand more about. So there's several parts. He wants to hear more about QKD adoption, and it varies greatly between the U.S. and the rest of the world. Standards and alt PNT. He's also very interested in hearing about this. This is the second part about PKI standards development. So, and so guys. So one thing, especially to this gentleman, please email me offline. You can do president at industrynetcouncil.org or info at industrynetcouncil.org. It'll get to me. So I am doing 2 talks myself on on MLDSA and certificates and what enterprises should do. If you are interested in participating, and in fact, that is the reason we have this whole group, is so enterprises can get involved in the standards body. Please talk to me. And we will also have NIST speaking on this whole area. We will also have, as I say, Dr. Vadim Lubashevsky. He is one of the co-authors of MLDSA. He will be talking. You ask him yourself. There's also SLHDSA. I know. But please, if you're interested, PKI and the standards, just talk to me offline, and I will go into more detail than you ever wanted to know about all this stuff. I am very concerned. There's so much stuff going on, and it's I don't want to take up Bruno's time with all that. We will also have a specific session on QKD. We have 3 QKD vendors. So Bruno is setting the stage. It's like, so if I'm telling you, this is 101. We gonna be deep diving into each of the areas that he wrote about. So if you have anything that you want deep dive more on, we can get you the people. Bruno, I'm sure, can deep dive on any of these topics too. Just contact me. So Bruno, do you want to talk any more about what I'm blabbering on?
Sure. Let me just say like 1 or 2 things quickly. QKD adoption, I think I have a slide back here. This memo has really made a strong case against why QKD should be adopted. If you want to see why, I encourage you to check it out. Adoption, I think, in the US has mainly been within like these banks, but globally it's very different. Like South Korea uses this for hospitals, for example. So I think this is really a largely fallout from this NSA memo and the real concerns that it highlights here. Which, by the way, before you hear a talk on QKD, you should read this memo and think of some questions.
So
Um,
Bruno, please send me a link to that thing. And before we do the QKD, when we do the announcement, I'll put that out for people, so they have it. So um, eh, so let me. This is, I think, a good one for Quantum 101. Where do you see quantum entanglement in real life? Can you give any examples of real entanglement? That's a tough question, I know. We don't
so,
live in a entangled world.
well, actually, I would say that we do. Like,
Really?
if you think about these, we don't think about entanglement because we are very, let's say, macroscopic creatures, right? We don't live at the level of atoms. And if we want to use entanglement for anything useful, we really have to be manipulating individual entangled particles. But entangled systems are everywhere. Whenever you interact with something, some people say that this is an application of entanglement or something like that the whole universe is entangled in some huge quantum state. There are a lot of people that believe that. Whether you do or not, I don't know. But it's not that entanglement is some esoteric thing that doesn't exist in real life. It's just that harnessing it precisely is really difficult, right? Like lightning, electricity exists in the real world, but using it to do
Mhm.
computation is a very different story, right?
So, one thing I used kind of to explain entanglement, it's like me and my daughter. My daughter I'm in San Francisco, let's say my daughter's in LA, but then I get like, wait, she want me call her. She want me call her because we're entangled at the heart level, you know? And so then when I call her, she's like, oh mom. But then of course that could be because she's always, you know, she's always that way. But I'm just kind of trying to, it's like it's a very hard concept to understand, I think, entanglement, but it's amazing. I guess the only thing I can say about some of this quantum stuff, and you tell me if you think is right, is like a lot of times we don't actually know how it works, but we know that it does work. Would you say that?
Yeah, I would kind of say that. I would say that I don't really know where entanglement comes from. And some people would say that there's no where, it just is, right? It's just that is the physics of how our universe behaves. But we understand how to manipulate it, how to think about it pretty well. And I would say that that is pretty accurate. Yeah.
We know how to use it. We
We know.
don't necessarily, yeah, but it is mysterious. It is mysterious. I'm sure someday the day will come when we understand it at a deeper and deeper level. But it's very powerful that we can use it today. Just that statement in itself. The reason we're having this quantum series, I see this as transformational. But I'm going to give you one aspect of GPS. Just this morning, I was talking about, I was reading that, like, you need now a warrant to get geolocation data. How people getting geolocation data, is on your phone, and so if you and Google was storing it, so they do a warrant to Google. But if it just on your phone, it not leaving no phone, how you do warrant? I guess you got to do warrant on the specific phone, but you can't
Right.
do something like geofencing. That this is going to be a transformational set of technologies. So, can you talk about what's commercial now, what's approaching commercial? We can also keep track of that. If you guys like, at INTC, we can keep track of like what's going commercial.
Yeah. So I would say QKD systems are commercial, have been commercial for a long time, since like the 2000s, with varying levels of quality and cost. Um, Quantum computers are becoming more commercial. I mean, a quantum computer essentially is a supercomputer. So the same way that some people sell supercomputing time on clusters, there are various companies like IBM and Google, Quantinuum, IonQ that sell computing time on their platforms as well. So that's commercial. But in the sense of a thing that I can buy as a consumer and like use, then you just have to think, what is quantum, right? If you want to do some very simple quantum experiments, you can buy like a laser pointer off the shelf and put it through some glass and do something cool. But useful applications of quantum computing, as far as I'm aware, I can't really think of anything that you have like a little quantum box that you buy and it does something useful for you. Maybe like a quantum random number generator, but I wouldn't want to buy that.
No, actually, there's a lot of people that are giving free time. I think Oak Ridge, you have to tell them what you want it for. IBM is like, if you want to work, and it's super interesting, I think, because, like as a developer, trying to, you have to shift your mind around. So if any of you guys are developers, I encourage you to start playing around with, quantum playgrounds and stuff. I'm gonna shut this off by there's so many questions, and what I will do is I will send the questions to Bruno if I didn't get to yours, and we'll see if he can answer them offline to you. And again, I encourage you guys. Bruno, if you can stop sharing for a second, and yeah, and I'll share mine because I super, super encourage you. Hold on, let me share mine. I super encourage you to come to all the other ones because a bunch of the stuff that there's questions on is what are the PKI standards, all that kind of stuff, even the harvest now, decrypt later, all that kind of stuff. That will be in this next talk. And as I said, I encourage you to if you have questions, thoughts, whatever, please please hold on. There's somebody who wants to speak. I'll let him speak in 1 second. And so let me see. But I do have one comment from in the chat window. It says this is one of the best overviews that they have ever seen of this whole field. And I really want to echo that, Bruno. Thank you so much, for doing this. It has been incredible. There's every slide could be an hour long. So I really am very grateful to you. Mike, did you have anything you wanted to talk about?
All I was going to say is what you just said and what you referred to the previous caller as saying. This was a great presentation, a whole lot of information in a short amount of time. Bruno, thank you so much. And Nalini, thank you for putting this on, and hopefully much more to follow. And I hope we can stay in touch with Bruno. Thanks again to everybody. This is something enterprises need more than we even know. And thank you.
Yes, Mike is the president of INTC. So thank you to him and Alvaro, our board chair, and Drew, our secretary and co-founder, for helping with this. And Bruno, I hope that we'll get you to stay involved with INTC, maybe do a SIG, something like that. So guys, if you're interested, if we want to do something like a quantum special interest group, just email me. Okay, because that's probably kind of the thing we may be going on, but we'll brainstorm. Thank you all so much. Bye.
Thank you.